Assalamualaikum and hi. My name is Wazam Aiman bin Wazukifli. My matric number is DE240154. This is our group member.
For the introduction, this project focuses on the design and analysis of the PID controller for controlling the speed of a DC motor driving a blade load. DC motors are widely used in industrial applications because their speed can be easily controlled by adjusting the input voltage. However, load variations such as change in inertia and friction can cause speed instability.
To address this issue, a feedback control system using a PID controller is applied. The DC motor and blade system is mathematically modeled by considering both electrical and mechanical dynamics, and the model is implemented using MATLAB Simulate. Manual and automatic PID tuning methods are then applied to improve the system response. The performance of the system is evaluated based on time domain parameters such as overshoot, rise time, settling time, and steady state error, demonstrating the effectiveness of the PID controller in improving speed stability.
Hello and good day. My name is Garrett Ivanhoe and my matrix number is DE240164. And today I will be presenting about the manual calculation. So this is manual tuning of PID gain. So first we need to determine the characteristic equation CE above block. So the equation is 1 kgs HS equal to 1.28 K over 0.0537 S cubed plus 4.9732 S squared plus 1.6392 S. So the equation will equal to 0.0537 S cubed plus 4.9732 S squared plus 1.6392 S plus 1.28 K equal to 0. And we compile it into the table. So by using cross multiply, we get the alpha is equal to 4.9732 times by 1.639 minus 0.0537 times by 1.28K over 4.9732. To give an equation a stable condition, so first, at 0.1511 minus 0.068736K over 4.9732 is less than 0. So after we simplify it, so K is less than 8.1511 over 0.068736. So K is equal to 118.586. Yeah, So next for B, 8.1511 minus 0.068736K over 4.9732 times by 1.28K over 8.1511 minus 0.068766K over 4.9732. So B is equal to 1.28K. So next, 1.28K is more than 0, so which means K is more than 0. For stable condition, 0 is less than K and less than 118.586. So the value of K critical, which is KCR, is equal to 118.586. So next for K, which is KCR, from the equation 4.9732 S squared plus 1.28K, so we substitute the value of K equal to 118.586. So the answer is 4.9732 S squared plus 151.79008 equal to 0. So next, we find the value of S squared, which is equal to negative 30.522. So for S1 and S2 is equal to plus minus square root 30.522, and the final answer is plus minus 5.5247.
Good day, my name is Benedict Pengzihao, DE240117, and I'm going to talk about the sustained oscillation at the limiting value of K equals to K critical is 5.5247 rad over second. Thus, P critical period oscillation equals to 2 pi over omega is also equals to 1.14 second. And the PID type we have P, PI, and PID. So for P, the KP is 59.293 and the TI for P is infinity, whereas the KI, TD and KD is P. And for PI, the KP is 53.3637, the TI is 0.95, the KI is 56.1723, the TD KD is 0. And for PID, the KP is 71.1516, the TI is 0.57, the KI is 134.827, the TD is 0.1425, and the KD is 10.1391. And table 1.0 shows the gain of PID controller as tuned manually using the Ziegler-Nicholas closed loop. Experimental oscillation testing was done to determine the ultimate gain K critical equals to 118.586 and ultimate period PCR is equals to 1.14 seconds. The proportional only P control gave KP is, as mentioned earlier, 59.293. The proportional integral PI control gave KP 53.3637 and KI equals to 56.1723, and the full PID control gave KP is equals to 71.1516, KI 124.827 and KD 10.1391. These values are the theoretical initial tuning point of the PID before fine tuning.
Assalamualaikum, my name is Muhammad Amin Kamal, my meter number is DE240155. So I will show you about the block diagram for this task. So we have two input, which is 900 RPM and 1500 RPM. So for this block diagram, we have subsystem on it. So for the subsystem, we have two transfer function and one gain for this subsystem that we got from the DC motor data that has been given in project instruction. So after we run the simulation, we got the result for this simulation. So as you can see for this result, which is for the orange line, that the input for the 1500 RPM and the yellow line is for the input 900 RPM. So for the green line is the output for DC motor 1500 RPM, and for the blue line is for output for DC motor 900 RPM.
So, Assalamualaikum, my name is Ahmad Rishad Asmawi. So, next I will present the second task, which is the manual tune PID control. So, here is our block diagram. So, as you can see, there's two input, which is 1500 RPM and 900 RPM. So, for the block diagram, we use the same as before, the subsystem for the DC motor, and then the control is by PID. So the first one is controlled by P, the second one is controlled by PI, and the third one is controlled by PID. So we substitute the value on previous calculation. So then we run the block. So as we can see here, the output. Okay, so here the output. So the yellow one is the input source 1500 RPM. The blue one is the DC motor controlled by P only, and then the orange one is controlled by PI, and lastly the green one is controlled by PID. So from the result, the DC motor controlled by PI is more aggressive than controlled by P only. And then next is for 900 RPM input. So it's also same, the block diagram is also same like before, just change the input from 1500 to 900 RPM. So as you can see, the result like must be always same, because they only change the input. So just like I say, the input and all DC motor is also same. So Assalamualaikum, my name is Ahmad Rishad Asmawi. So next I will present the second task, which is the manual tune PID control. Okay, so next is for the comparison for the manual tuning and auto tune. So here is a block diagram. So as you can see, the input is 1500 RPM. The subsystem is use the same as before. So this controlled by PID. So now I will show you how to tune the PID. So here is the PID we get from manual calculation or manual tuning. So we just press the tune button to tune the PID. Okay, so the graph, here, this is what it's look for the tuning. So here, so this is the graph before. If we adjust this one for the response time and transit behavior, we can know that our graph will be looks like what. So like now I will do like this one and this one. So here the overshoot is less than before for the dot line. This is our manual calculation, manual tuning, and this one is for the auto tune. So we make it more less okay, like this one. It less overshoot than before. So as you can see, the show parameter for the tune, this is for the auto tune value. So here and then for the block, this is our manual tune. This is the comparison between the rise time, setting time, overshoot, and peak. As you can see, the overshoot for manual tuning is 50%, but when we auto tune the PID, we get the overshoot is 0.19%. So now we will apply and then we will see the output. So now we update the PID into the block. So we close this one. So now the PID already update to the PID controller. So now we will run the system, so we can see the output different. So let's see scope. Okay, so here is the output. The blue line is the input of source 1500 RPM, and then for the yellow one is the manual tuning. We get PID from the manual calculation, and the orange one is the auto tune PID we get from auto tune. So as you can see, the graph from auto tune is more stable than manual tuning. The manual tuning is more overshoot than auto tune. So here is the result. Okay, so next I will present about two PID controller response, which is manual vs automatic tuning. The table show a clear performance improvement when using automatic PID tuning compared to manual tuning. With manual tuning, the system exhibits the very high overshoot of 50.76%
indicating excessive oscillation and poor damping, whereas automatic tuning drastically reduced the overshoot to 0.19%, resulting in much smoother response. Although the peak time TP and the rest time TR for automatic tuning are slightly higher than manual tuning, the difference are small and acceptable. Most importantly, the settling time TS, which is plus minus 5%, is significantly reduced from 2.42 seconds for manual tuning to 0.319 seconds for automatic tuning, showing that the automatically tuned system reach steady state much faster. Both methods result in a stable system with negligible steady state error (ESS). Overall, automatic PID tuning provides superior transient performance, faster stabilization, and better control quality than manual tuning.
To conclude this project, we focus on designing and evaluating a PID controller to regulate the speed of a DC motor using MATLAB Simulink. From the simulation result, it can be seen that the controller performance strongly depends on the tuning method used. The Ziegler-Nichols manual tuning provides an initial controller setup but result in a highly oscillatory response with significant overshoot. In comparison, the automatic tuning method produces a much more balanced response with quicker stabilization and smoother speed tracking. Overall, this project shows that while classical tuning methods are useful for analysis, automatic PID tuning is more effective for achieving stable and reliable speed control in practical application.